against the tide. I wanna forget you, but you pull me in. I know this ocean is far too wide. I wanna forget you, let me forget you. Push and pull, but you repel me, giving up this fight. Love and hate, we've blurred the lines. I'm giving up this fight. You've lost, but I don't feel I have won. I wanna forget you, but only time will heal. Too late to erase the bad we've done. I wanna forget you, let me forget you. Push and pull, but you repel me, giving up this fight. Love and hate, we've blurred the lines. I'm
Hey, hello, what's up, guys? So, this is Vignesh joining you all for the third episode of the My Factory series. This is going to be an interesting episode. So, I went through all your problem statements. But I thought I would do something interesting today. So, let me tell you what. Before that, for all those who are joining today newly, so this is where we build product architecture live in the stream. So we basically take up your problem statements and build the architecture for the same live in the stream. So that's what it is all about. So I had basically shared a form where you can fill in all the problem statements you have, and yeah, I would be basically architecting it live. So that's what the series is all about, as you might already know. Today we are going to do something different. Hi bro. So we are going to do something different from what we did before. So what we are going to do is, since I didn't find any of the problem statements so far which I received challenging, so what I thought was, okay, maybe pick a company which already exists, like for instance Google, Facebook, Amazon, Yahoo, Flipkart, pick some already existing company and try to reproduce their architecture. I mean, I won't be accurate enough. Like, let's assume I am to design my own Facebook, my own Google, my own Flipkart. How would I go about architecting that? Considering the technologies I know, it's not. I'm not going to talk about what technologies Google uses. So that's going to be another topic. All the way. But what I was thinking is maybe I will pick a company which is shining in the market, big giants. Okay, let me take Google for this session. Maybe let's start with the big giant. So I will basically architect how Google can be made for today. Like I won't be able to exactly say this is how Google works, but I will try to research. That's what we will try to do today, because I didn't find any problem statement challenging. So in case you have any challenging problem statement, let me know. I will take it up and I will architect it live. So with that, let's get started, because we are going to architect Google, so which is going to take a lot of time today. Lot of thinking as well, so a lot of planning. So let's architect Google. So I am going to quickly share my screen. So in case you have any questions, feel free to share all that in the chat. I will be responding as and when I do things. So I am showing my screen. And yeah, here we go. So this is my screen, and I am going to open up my drawing board here. So this is my drawing board for today, and we are going to do Google search. Google has a lot of products and we are going to focus on search. So I hope you are able to see my screen. Yeah. So let's define our goal. So what we want to basically do is we want to develop a Google search. So it already exists. There is no point doing it. The main agenda of today's session is to basically understand how do you go about designing complex systems like this if you were to do all of it by yourself. So it's a challenge for me also, because I have not done it before. So I'm doing it all live in front of you. So even I don't know. So there is Google search on one side, and there are websites containing information on one side. Websites and other sources of data. Website is not the only source of data from which website is not the only source from which Google picks up the data. There are websites, there are other things like GPS location. It takes up the location information. It takes up user reviews. So Google picks up information from multiple places, right? So it picks up information from books, so videos. So there are lots of sources of information. So let's classify this as information. So I am assuming that I am Larry Page today. So and I am designing this system. So I am designing the first Google. Let's assume that way. So that way I don't have any preconceived notions or thoughts. So yeah, any questions you have, just drop it down in the chat. I'll open my chat window as well. So I have sources of information. So and what I want to do is I want to basically since I am a search engine, what I have to do is crawl all this information. I have to pick up all the information, right? So I need a crawler or a bot. I need bots or agents, so which will basically crawl for information. So, or let me call it spiders, that way it is very much evident. So these spiders, the main responsibility of the spiders is to basically crawl for information from multiple places. So I spawn multiple spiders. So I have not looked at any reference. I don't know how Google currently is operating. I have but these are all some basic assumptions which I am working with. So, and let's copy the same. So you have multiple spiders like this. So you have a lot of spiders. Okay, let's create one more to fill the gap. And any question you have, just interrupt me anytime. And now this function of the spiders is basically to probably crawl all the information. So I don't know what algorithm Google uses. I don't know what storage Google uses. Yes, I have read some information, but I don't know whether that is credible, because to be honest, I have read a lot about how Google does things, but a lot of the information is outdated. If you go to highscalability.com, they have some information, but that's dated to 2008. That's not the way they do things anymore. Spider cluster, let's call it this way. So there are groups of spiders, basically scanning multiple websites. And what I have to do is so these spiders are going to crawl for the links in my page. So, and it has to basically after crawling the page, it has to store the metadata somewhere. So I am going to have a metadata database, so which will basically have nothing but or let me call it distributed metadata database. So it's going to have all the things basically from all the websites. Let me it is not two ways. So the website don't contact the spider contacts the website. So this arrow is fine. So the spiders write data to the distributed metadata database, let's say, and there is going to be a lot of these. So since this is distributed, now these are all my assumptions. So don't assume that this is how Google works. So these are all my own assumptions on how we can basically design our own Google for this. So I have a cluster of databases. Let me just delete this. So so what we are doing is we want to basically do the search, right? So what we get is when we do the search in the UI, we are going to basically send a request to the Google server. So again, if you notice, Google has something called as a global load balancer. So let's call it that way. So you can read up on what global load balancer is. So it's basically nothing but a distributed load balancer across multiple regions, in multiple places, but has the same IP. So, but there are regional Google websites as well. Let's do this way. So regional or global load balancer, because if you go to google.co.in, what you are going to do is you are going to hit the Indian regional load balancer. If you are hitting google.com, you are going to hit the global load balancer. So that way the load is distributed. So I am doing a Google search. So now this is a two-ended arrow. Okay, I have a load balancer here. Now what I want to do is I have I am sending this request, and this request has to go to some server, right? And I can't have a single server, because if I have a single server, single Google server per se, then things will fail, because a lot of searches are going to come at rapid paces. So what I need is microservices. So I have multiple search services. Let's assume we have multiple search services. So let me copy this and let me copy this. So we have multiple search services, and what of course the service don't come first. First, the load balancer has to come to a cluster. Like in Google's case, it is Borg or Borg, however you call it. So there is Borg here, so which is hosting all these services and database. So in today's world, if you are using an open source tool like what is available in the market, you can use something like Kubernetes or Mesos. So that's what we are doing today. So which component here will handle the concurrency? The load balancer. Yes, the load balancer will handle. Load balancer is just to receive and distribute the request. To the respective service or respective endpoint which has to serve the respective request. So basically, if you don't want a single bottleneck, right? So that's why this load balancer exists, to basically distribute all the traffic to multiple services. This load balancer doesn't do anything like concurrency. So concurrency happens. Load balancer does receive all the requests parallelly, of course, yes. But then all the requests are processed parallelly, through the services behind the scenes. So since we are using microservices, all the requests are processed parallelly, and responses are given parallelly. So there should not be any bottleneck. If there is any bottleneck, then things will start falling apart. So let's do one thing. So we have the load balancer. So now the load balancer has to hit the respective search service, right? So let me just put an arrow like this. It can hit any one of those search service. So depending on your proximity. It's not random. So it also depends on the location from which Google is making the search result. For instance, if you are in India, you will basically hit the search service running in Indian region. So these services will run in multiple regions. So let me declare it like this. So to back, okay. I guess I have to start using layers. Anyway, I don't want to make things complicated. I will just put a text here. So let's assume this is APAC, and you have one in the US, a set of services in the US region, because your responses have to be fast. If you go between region to region, if you are hitting a server in US from India, it will take close to 300 to 400 milliseconds for the entire round trip time. So you want to avoid that. You want to give the fastest search result. So you have distributed services across different regions. So, and you have, let's say, Europe, something, okay. Let's say China. No, that comes under APAC. So let's say Europe. I don't know. So some region. So they have regions like these where the services are distributed. Now, what are these services going to do? Now it has to basically go and see if it is in the hot list. Like meaning, let's assume this search result was requested by many people. Like for instance, COVID is a result which many people are asking for to Google. So what it must have is, it must have a caching layer. So cache, let's say that too distributed cache. You can't have a single cache. You need to have a distributed caching system. In memory cache for frequent queries. So that can be something like Redis or whatever they are using. I don't know what they are using. Maybe a custom developed solution by them, but you have a distributed caching system to give the frequently searched result. It will basically pick up the frequently searched result and go to the respective server and then get the result from the respective database. So what will basically be stored in cache is nothing but the frequent term. For instance, COVID is a frequent term, and if I type COVID, okay, what are the list of websites which I should return for India? What are the, and also it is location aware, right? So for if you search COVID from India, so then the search result differs from if you type COVID from US. So you get location aware search results. So it's not just one global result for every region. They have specific search result depending on which region you are coming from. So they might have a cache like this where they are storing frequently search result. So next layer would be, okay, they have a cache, and okay, let's assume it's a cache hit. So if it is a cache hit, then it will basically get the URL from here, and so what it will do is, so let me tell you about this. So like for instance, every metadata database will have a unique ID. Let me call it index ID or index. Yeah, some ID. I didn't work at Google, so I don't know how they did it, but I am assuming things. Lot of assumptions here. And of course, there are some things which I have not talked about. I'll talk about that as well. So, okay, first thing is distributed cache for query. So then what it will do is, if it's a hit or miss, depending on whatever it is, so it has to pick up the metadata from the database. So if it is a miss, it has to go to the database directly and search for the respective metadata. I mean search term. So and how will it go and search the search term? The database is partitioned by alphabet. So index ID, partitioned by let's say alphabet, and maybe location. So partition by alphabet, geolocation, and they might use some other partition as well. So let me just start with this partition for now. So each database is partitioned like this because you can't have a huge database. So you need to have some sensible size, right? So that's why all these databases are partitioned. Let's do one thing. I'll pull this out. I'll add it here. So at least it's a bit clear. So you have a partition database like this, with geolocation and alphabets or any other partition key for that matter. Now the important thing is, so let's say it searches the cache, it finds the cache, fine, it goes directly by index ID. It doesn't find in the cache, then it has to go to the respective database depending on the partition, depending on the alphabet. Like for instance, if your search term starts with A, so whatever search term starts with A, the indexes might be in a specific database. Search term starts with B, the indexes might be in specific database. So they might split by alphabets. So and they will pick all the metadata. Like metadata is not the information per se. It's just it's not the complete information. It's rather the URL. So what information would be typically stored? So maybe URL, the rating, and the tags or metadata. And maybe top 5 frequently occurring terms, backlink rank, and all that. So you have a relational database. You have more things. I am not going to cover the database schema now. So we will talk about that later if we have time. But so they have a database having the metadata of all the websites. So then what we have is, so let's say it is a cache hit or miss. So depending on whatever it is, so they should have this is a background process, whatever I am talking about now. So this is a ranking engine running in background. So the ranking doesn't happen real time. So all these websites are ranked in the background. So there are a lot of algorithms which they can use. So I don't know what algorithm they use. You think that it is page rank, but it is not page rank. So it is their own custom algorithm which is completely proprietary. No one knows what it is. So let's assume for now it's a ranking engine running in the background with all the algorithms. Now the only job of ranking engine is to basically pick up data from this database, from this metadata database, whatever is not indexed. So whatever is not ranked. So initially, whenever the spiders come with all the data, so let's assume it stores in the database, with a flag saying that it is not ranked yet. And this ranking engine regularly goes and reads the distributed metadata databases, and what it does is it sees whether the content is ranked or not. If it is ranked, all is good. So if it is not ranked, then what it will do is it will basically use all the terms, all the tags, all the backlinks and everything, all the information the website respectively has, and try to achieve the rank. So or it can happen at this stage itself. So so it can happen at this stage because the spiders are coming up with all the metadata information, right? So when a spider is coming with all the information, so the ranking can come, and then the final ranked result can be stored in the distributed database. So let's do it like this. So let's assume the architecture is not like this. Let me move this down. So rather, all these spiders come with all the information. It comes to the ranking engine first. All the data comes to the ranking engine first, and now this ranking engine, it's not running in the background, so now it is a real-time ranking engine. So now what this real-time ranking engine can do is, as and when spiders come, each and every spider come with information. So again, this ranking engine has to be distributed. So distributed real-time ranking engine. So as and when spiders come with information, so it looks at all the information which it has arrived with and gives it a score, and then final score is basically stored in the distributed metadata database. So let's do it like that. That way, you don't have to do anything. Like in case you have to reindex the information, in case you have to re-rank things, so what you have to do is you have to just spawn a spider again to the same website. The spider will come with the information. Then the information is being passed to the ranking engine again. So the ranking engine knows that this data was already ranked. Now let me re-rank it based on the previous history as well as the the new data which has come in. So that's how it can basically do. So let's assume these spiders run in a schedule. So scheduled spawn. So meaning, what I mean is, so let's say you have a database like this, saying these are the databases to be crawled. You have a database, this is again a distributed database, so these are the databases to be crawled. So let's assume that the spider cluster picks up information from this database, which is nothing but the database to be crawled, and then it goes to the respective website, crawls the information. Then what it does is it basically gets the data, pass the data which is retrieved to the ranking engine. Now the ranking engine sees whether there is any history or whether it is a new result, and it also looks at other factors like how many backlinks this website has, how many reports this website has, and all the other information like how many is it a business, and all the information. Then after all the analysis is done, then the final result is stored in the distributed metadata database. That's it. That's pretty much it. So in fact, now it has to whether it is cache hit or miss. So depending on that, the search. Let me just put it like this. I will remove the arrow for now. So this search service can hit the cache, will hit the cache, and if it is a cache miss, it will hit the distributed metadata database. So now looking at the file system, because if you notice one thing, there are going to be a lot of databases, one to store the data of websites, list of websites to be crawled, another to store the website metadata itself, another to basically have the information of the ranking So you have lot of things, right? So you have lot of data which is to be stored. So one important thing is, so you can choose any database, but ultimately this database is going to store your data in your file system. So if your file system is not tolerant enough, if it is not distributed enough, then it's going to go to a toss. So what you need is a distributed file system. So that's needed. So all of this is stored in so for Google they call it Google file system, GFS. So all this data is stored in Google file system. So it can be anything else in your case. So a distributed file system, and on top of this what you also need is a good monitoring system. So you have lot of services like this, so you need a monitoring system to basically monitor if any, let's assume a spider got stuck in a website. So what you need to do is you need to have cleanup jobs to basically clean up the spiders which take long time to basically crawl a website. So there will be timeouts for each and every spider. So you can't ask your spider to keep crawling a website forever, right? So if your website is having, let's say, infinite loops, meaning link inside link inside link inside link, so the spider is going to keep crawling everything, but it is not going to reach any result. So in such cases it's going to be compute intensive. So spider needs to have timeouts, and there needs to be cleanup scripts, there needs to be monitoring, there needs to be tight security in place. So it's so these are all the other infrastructure you need to care about. I am not putting that in this architecture because it is already huge. In fact, this is not the Google architecture. They will have more components in this. So for instance, if you are searching something, let me just show you in Google. If I am searching for COVID, so what I get is something like this. I get a map of cases, I get cases overview in a different layout, in a different layout, in a different layout. So for instance, the Google website layout changes as per the search result. If I go to the same Google and search for Timecampus, I get a different layout. I get the map of the business, I get the business name, I get reviews, I get an option to edit this business because I own it. So, and if I go and search for, let's say, calculator. So, okay, this is interesting. Yeah, you get a Google calculator. So, which is interactive. So, Google is basically what it is doing is, depending on your search term, it is changing the way it is rendering the user interface. So, all this also matters. So, you have to process the search term, understand what meaning it carries, and then finally render the UI depending on what it is actually. So, this is how all the decisions go. So, there is a huge amount of things to be considered apart from this. This is just the beginning. So, this is how you start off. And then finally, you have, so every service is exposing API. So this search is hitting the APIs and you are getting the result. And if you notice one more thing, if you go to google.com and you view the source, you see a minified source. So you can, what you can do is, unminify online. So if I just copy this here and I put it here, I don't know whether it can unminify. Let's see. Or I can do it here itself, I guess. So I will go to inspect element. What I will do is, yes, of course, and one more thing is it changes the way in which it works depending on the device as well. That also matters. So this is how Google is. So it has a lot of scripts running, and it has a lot of styles and everything. That I am not worried about styles, but what you want to see is the network. Yeah, so the network request. So let's say I search for Timecampus, the search which I did before. So what it is doing is it is making a GET request. So it is going to make a GET request to okay, it's making a lot of requests because it has to get a lot of images. And if you notice, all these images are encoded in base 64 format. It is not a URL, rather it is a base 64 encoded image, so that they can avoid HTTP requests to and fro. Because let's assume they make HTTP calls for each and every image they have to load, so which means that it's going to be returning the result at a very bad timing. So what you need to do is, as they have done, so you need to base 64 encode all the images as well. I mean, you need to store the base 64 encoded version. So, and we saw the search result somewhere here, right? Yeah, here it is. Okay, this is interesting. Okay, now here is the request and response. So they are requesting the search term like this with lot of hash values and everything to prevent injection and to prevent things like what do you say, cross-site scripting and everything. But you, and also it carries things like cookies and everything. So every browser stores cookies, device information, so they encode everything and basically send the information. So and you are getting a response as well. So let's look at the response. So now if you see the response, what they are returning is, response is neither a JSON nor a XML. So what they are returning is, they are directly returning the complete HTML page itself, because it is a GET request. So what they are doing is, they are calling, they are making a GET request, and they are doing all the rendering on the server side. So they are using server side rendering. So they are using server side rendering, and finally whatever response they get, they are returning it back to us. So that's how they are doing things. So with that, I hope you got an idea of how Google architecture basically is, how they have basically done some coding. I mean, you still have a lot more things. Maybe we can split it into multiple sections if we want, but this is how things actually work. So if you have any doubt, let me know, but otherwise we can probably split this same thing into multiple sessions, or probably take up a different website, different company, different giant in the next episode, if you don't have any challenging problems. Because it doesn't make sense for me to share something like website development with all of you. So what I want to do is share something which is really useful for all of you. So I hope this was useful. So see you again in the next episode, which is going to be on next Tuesday. So tomorrow it's going to be product development. So I guess what is for tomorrow. So let's see what is for tomorrow as well before we go ahead. So we will be having knock. So season 1, and it's going to be ouch. So it's HTML, CSS and JS, I guess. Yes, we are in the 4th episode of product development, so we'll be talking about deep. Okay, I'm not going to talk about the theory behind it. We are going to go deep into HTML, CSS and JS. So see you all in the next episode. Thank you for watching today, and see you all again. And yeah, so let me quickly see if there is anything else I missed. So solution, validation, iterations, and yeah, these are my details. Let me hide the chat box, so in case you want to get in touch with me, you can always get in touch with me. So bye bye.